Push that rock here, Simpson math. Let's graph the natural log function. Now remember, this is log base e of x. So the input is x, our base is e. We're looking for when we put in an x, we're looking for an output that is an exponent on e that gives us the x. So an easy one would be 1, because we know that when you say e to the 0, any non-zero number to the 0 power is 1. So therefore, natural log of 1 is 0. So that gives us an easy output. When you put in 1, you get out 0. Now, one thing we need to keep in mind is the argument must be greater than 0. So that's why I've only graphed the positive side of the x-axis, because the argument must be greater than 0. So when we're thinking about inputs, we do need to think about inputs close to the domain restriction. So like a number close to 0. Well, what I'm going to choose is something like this, 1 over e. Well, that's e to the negative 1, right? E to the negative 1 would be 1 over e. And whatever e to the negative 1 is, it equals e to the negative 1, or 1 over e. So the natural log of e to the negative 1 is equal to the exponent you would put on e to get e to the negative 1. Well, that's clearly negative 1. Now, obviously, e to the negative 1 gives us this input here. So that makes the output kind of simple. And now 1 over e, is about 1 over 2.7, remember? So it's between a third and a half. So, if a third's here and a half's here, it's somewhere in here is 1 over e, and we get out an output of negative 1. Now we can play this game all day. I can put it 1 over e squared. Well, then that means I'm going to get negative 2, because negative 2 is the exponent you put on e in order to get 1 over e squared. So the closer I get to 0, so 1 over e squared is going to be even closer to 0. The closer I get to 0, the further down the graph is going to go. So I have a vertical asymptote. So there's a vertical asymptote that is the y-axis, or we could say x equals 0. Now, what about as the x values grow? Well, I'm going to put in e. E's about 2.7, so if this is 3, e's about right here. And of course, the power on e is 1. E's, of course, the first power of e. And then we can put in e squared, and we'll get out 2, because the natural log of e squared must be 2, because e to the 2 equals e to the 2. So when now e squared, remember we did that a couple of weeks ago, it turned out to be about 7. So if this is 3, 4, 5, 6, here's 7. It's a little bit bigger than 7, so here's e squared. And so when we get way over here, we're at 2. Now remember, e cubed is about 20, so I have to go way off the page to get to 3. So it grows very slowly, and this is a key characteristic of logarithms. Exponents grow quickly, logarithms grow slowly. And we're going to use that characteristic to help us evaluate logs that are difficult to evaluate. So this log has a vertical asymptote at 0. It does not have any kind of end behavior asymptote. It looks like it does, but it grows without bound. Dirichlet said the natural logarithm marches to infinity with dignity, meaning you have to go really far out on the x-axis to get big values for y. So it's a very slowly growing function, but it does grow without bound. And there's the natural log curve. Math made simple. Simpson math.